Chapter 8, Atomic Structure. In this chapter, we're going to apply Schrödinger equation to atoms, starting with hydrogen atom. Due to the mathematical complexity, we're going to omit the derivations, but focus on the results. Let's start with hydrogenic atom. A hydrogenic atom is an atom or an ion that contains only one electron outside the nucleus. For example, a helium contains 2 protons and 2 electrons. Now, if helium loses 1 electron, then it becomes positive charge, but only 1 electron outside nucleus. Similarly, lithium contains 3 protons, 3 electrons. When it loses 2 electrons, it becomes 2 positive charge, but still outside it only have 1 electron. So these are called hydrogenic atom, where you only have 1 electron outside the nucleus. The potential energy between the electron and the nucleus is described by Coulomb potential, which is negative Z is the charge times E squared divided by 4 pi epsilon r. R is the distance between the electron and the nucleus. Z for hydrogen atom, it's 1, because you only have 1 proton. For helium, it's 2. For lithium, it's 3. The Schrödinger equation says the Hamiltonian operator operates on the wave function, give the function back, times the total energy. For hydrogenic atom, the Hamiltonian operator is the kinetic energy operator, potential energy operator, which is the Coulomb potential. The Schrödinger equation we just presented in the last slide is in Cartesian coordinates. Due to the symmetry of atoms, it is more convenient to change to spherical coordinates. And in spherical coordinates, the Schrödinger equation can be separated into 2 equations. One only contains the 2 angles, theta and phi. The second equation only contains the distance r. It turns out that the first equation resembles the Schrödinger equation for diatomic rotation, and the solution of this equation is the spherical harmonic function that we already solved. And the equation contains 2 quantum numbers, angular momentum quantum number L and magnetic quantum number M. Solving the second Schrödinger equation give you the radial function. In addition, a third quantum number comes out, and that is the principal quantum number n. So the total wave function for hydrogenic atom contains 3 quantum numbers, n, l, and m. The total wave function for hydrogen atom is a product of 2 functions. The radial equation, which is a function of distance r, and the spherical harmonic is a function of 2 angles, theta and phi. The wave function is determined by 3 quantum numbers, n, l, and m. The quantum number L and m are already described in rotation. Quantum number n will be described later. Here we show 3 wave functions for the hydrogen atom. The first one, n equals 1, L equals 0, m equals 0. We can represent this function as psi 1, 0, 0. The important feature in this wave function is that it only contains distance r. It doesn't change with angle. So if this is the nucleus, the first wave function is the same for any angle. It's spherical symmetric. As we learned in rotation, when L equals 0, in chemistry, the convention is this is called s orbital. For the second wave function, n equals 2, L equals 0, m equals 0, we call psi 2, 0, 0. Again, you can see the function is a function of r. It doesn't have angle, and therefore it's spherical harmonic, spherical symmetric. And the third one, n equals 2, l equals 1, m equals 0, and now you see it's function of distance r and angle theta. It changes with angle. In fact, L equals 1 in chemistry we call p orbital. We'll see more in the next few slides. Here we show a few hydrogenic radial wave functions. Remember, the total wave function is a product of radial wave function and the spherical harmonics. And these are the only radial part of the wave function. Here again, we show some hydrogenic atom total wave functions. Each wave function is determined by 3 quantum numbers, n, l, and m. For example, if n equals 2, l equals 1, m can be positive 1 or negative 1. So these two wave functions, they have the same radial wave function, but the spherical harmonics can be different, positive or negative I phi. Let's look at the radial wave functions of the first few states of hydrogenic atoms. The first one, n equals 1, l equals 0, and in chemistry this is called 1s orbital. The wave function decreases exponentially, approaches 0 when the distance increases. In fact, all wave functions shown here, they decrease exponentially and approach 0. That indicates that the probability to find the electron approaches 0 when the distance of electrons are too far away from nucleus. For the second wave function, n equals 2, l equals 0, the radial wave function is positive at first, and then change sign becomes negative. At a certain distance, the wave function becomes 0, and this distance is called radial node. So the first wave function has no node, but the second wave function has a 1 radial node. So how do we visualize it? We know that when L equals 0, or the s orbitals, the wave function is spherical symmetric. So we can draw a diagram like this one. Okay, spherical symmetrical. So the wave function is equal at any angle, all angles. But what about the second wave function, 2s orbital? And this can be visualized by this diagram, where the wave function positive represented by blue color, and then becomes red, that's negative. At a certain distance, we can use the white color to represent the wave function becomes 0. Now, in general, the radial nodes, the number of radial nodes can be calculated by n minus l minus 1. For example, for 1s orbital, n equals 1, l equals 0, so 1 minus 0 minus 1 equals 0. So for first 1s orbital, there's no node. For second 2s orbital, so 2 minus 0 minus 1, that gives you 1 radial nodes. And for 3s orbital, then 3 minus 0 minus 1, so you have 2 radial nodes. That's here. Okay, 2 radial nodes. We have seen quantum number L and M when we discuss diatomic rotation. In hydrogenic atom, quantum number L is called orbital angular momentum quantum number, which specifies the magnitude of angular momentum using this equation, which is similar to the equation when we calculate the magnitude of angular momentum for rotation. The allowed value is also similar to the rotation, but the maximum number of L is determined by the principal quantum number n. So when n equals 1, then L can be maximum L is 1 minus 1 is 0. Okay, now when n equals 2, 2 minus 1 is 1, so the maximum L is 1. All right, so the allowed value should be 0 and 1. So when L equals 0, and that calls 2s orbital. When L equals 1, that's 2p orbital. The magnetic quantum number m specifies the z component of the angular momentum, as we seen when we discussed the diatomic rotation. The equation is m times h bar. So the allowed value for m is 0, positive, negative 1, positive, negative, until positive, negative L. For example, when L equals 2, then m can be 0, positive, negative 1, positive, negative 2. So you have 5 orientations represented by this diagram. And the z component can be 0, positive 1, positive 2, negative 1, negative 2. And as we discussed before, this can be better represented by the cones, like here. Okay, so the z component are 2, 1, 0, negative 1, negative 2. Okay, so z component of the angular momentum can be precisely determined, but the xy can't be determined. This is the first wave function for hydrogenic atom. N equals 1, L equals 0. So when L equals 0, M can only be 0. And as we discussed before, this wave function is only function of distance. There's no angle in this wave function. That means the wave function is the same at all angles, and therefore it's spherical, symmetric, that can be represented by this diagram. Here is a wave function where n equals 2, L equals 1. And when L equals 1, this is a p orbital. So this is a 2p orbital. The wave function is not only a function of distance, but also a function of the angle theta. So how does this wave function look like? The wave function shape is determined by the angular part. All right, so this is the angular part of this wave function. It's the cosine theta. Now let's plot how does the wave function change with this angle. Now the theta is the angle between the z direction and the line from origin to the point. That's the theta. Okay, so let's calculate wave function at different angle theta. So in this table, we calculate when angle is 0, cosine 0 is 1. When angle is 20 degree, the wave function becomes 0.94, and you can see the wave function decrease until it becomes 0 at 90 degree, and then becomes negative. So you can calculate all the wave function at a 360 degree angle. So how do we plot it? We do polar plot. Okay, so in polar plot, we calculate the distance between origin of the point, the distance as the function. So let's do this as an example. So first you draw z direction. Here is the origin. So when angle is 0, that's along z direction, and the function is 1. So distance here is 1. Now when angle becomes 20 degree along the z direction, so let's say this is 20 degree, the value becomes, the wave function becomes 0.94. So we measure the distance 0.94. That's here. Okay, so this is the point at 20 degree, and then 40 degree. Let's say here. All right, the wave function becomes 0.77. So we measure the distance from origin is 0.77. So you just connect all these points. Okay, and that's how you get this one. So again, this is angle 0, and then 20 degree, the distance is the wave function. Okay, and then you change angle, you measure the distance, you connect all the dots, all right, and when the angle above 90 degree, and that becomes negative. Okay, so connect together and you get this typical double dumbbell shape that you see from the textbook of 2p orbitals. So a polar plot shows the direction of the orbital, the shape of the angular part. So what does this tell you? Okay, does this tell you the electron moving like this dumbbell shape surrounds the along this shape? Actually, no. This just tells you the wave function along all angles. What's the wave function? So wave function tells you the probability. So what this tells you is actually the most highest probability of the electron for this wave function 2p orbital is the z direction, because the wave function is the highest. And then the wave function decreases with this angle and becomes 0 at this xy plane. So remember, this is a 3D diagram. So this is a z direction, so that you have an xy plane. Okay, so along xy plane, you can see in this diagram the wave function is 0, and so this is a node for 2p orbital. And you can plot the d orbitals as a same way as we do here. You list a table and you just calculate wave function at different angles. So we have instruction show you how to plot this d orbitals. Okay. In the last slide, we showed how to plot the angular wave function for 2pz orbital. And we showed that along z direction, the wave function has a maximum value and decreases with angle until it becomes 0 at this xy plane. And this plane is called the nodal plane. Okay, so along this nodal plane, wave function becomes 0. In fact, when L equals 1, you have 3 orientations. So PZ is one orientation. You can have PX wave function. So for PX wave function, the maximum value for wave function is along x direction. And therefore, the plane perpendicular to this one is the YZ direction. So YZ plane is the nodal plane. And for PY, 2PY, and the maximum wave function is along y direction. So XZ plane is the nodal plane. Okay. Now this nodal plane is also called angular node, because these are the nodes for angular function. Okay. Remember, total wave function is a product of radial wave function and angular wave function. For a radial function, the nodes is called radial nodes, and the calculation is n minus L minus 1. That's the number of radial nodes. And so here, these nodes is due to the angular wave function, and these are called angular nodes. And in fact, when L equals 1, you have one radial node, angular nodes. So in general, the angular nodes is just L, equals L. So let's look at d orbital in the next slide. This shows the plots of 3D orbitals based on their angular wave function. And there are 5 of them. And each of them shows different colors. And the color means the wave function change sign. For example, for the first one, the color change, the wave function change from positive to negative to positive. Okay. Now, when wave function changes sign, there must be a place where the wave function is 0, and that's the node. So for this one, in between, you actually have a cone here. Okay. So the wave function along this cone is 0. That's a radial angular node. Similarly, on the bottom you have another one. So the first wave function has 2 angular nodes. Now similarly, the second one, you can cut through them along this direction, or there's another direction. All right, the wave function becomes 0. So again, you have 2 here, and similarly, you go through this direction. Okay, and the fourth one, these 2 are the here. Okay, 2 planes wave function are 0. So again, the number of nodes, right, equal the angular momentum quantum number L. Okay, and we know that for radial nodes, n equals L equals 1. And here we show for angular nodes it's L. So when you add together, the total node is n minus 1. And that's the total node for a particular wave function. Having looked at the quantum number L and M, now let's look at the principal quantum number N. Remember in rotation, the energy is determined by quantum number L. Here, for hydrogen atom, the total energy is determined by the principal quantum number N only, and the equation is here. Okay, 1 over n squared times these constants, and these constants can combine together, and the combined this value is called Rydberg constant that you have already seen in the introduction of our quantum mechanics. And the value is 109,677 for hydrogen atom in inverse centimeter. Now, if for heavy atoms, the reduced mass becomes the mass of electron, and this will be the value for Rydberg constant. So here is the energy diagram that only energy only determined by principal quantum number. Okay. Now, because under a certain quantum number n, you may have different L and M. That means different wave function may have the same energy. Then you will have degenerate energy levels that we are going to talk about later. From last slide, we know that the allowed energies for hydrogen atom is determined by quantum number n, described by this equation. And the lowest energy is when n equals 1. And so this is the minimum energy required to remove an electron from the lowest energy state, that's the ground state. Okay, this is the equation to calculate lowest energy, and also called the ionization energy. So plug in all the data: Planck constant, speed of light, 10 to the 10th power centimeter per second, Rydberg constant, inverse centimeter, and that give you negative 2.1787 times 10 to the negative 18 joule, which can be converted to electron volts, negative 13.598 electron volts. So that's the ionization energy for hydrogen atom, and also the lowest energy of the hydrogen electron of the hydrogen atom. And at other energy levels, the energy should divide by n squared, and therefore we can use this equation to calculate allowed energies for hydrogen atom: negative 13.6 eV divided by n squared. It's a common practice to call principal quantum number shells and the angular momentum quantum number subshells. So here shows a diagram of shell. N equals 1, we also call K shell. When n equals 2, we call L shell. When n equals 3, we call M shell. Now for the first shell, K shell, because n equals 1, L can only be 0, and that is we only have one subshell. Okay, so one subshell for the when n equals 1. When n equals 2, L can be 0, can be 1. So we have two subshells. Now when L equals 1, M can be 0, positive 1, negative 1. So you have 3 orbitals. 3 plus 1, that's total 4 orbitals. 4 orbitals can be calculated by 2 to the second power. Okay. Now for the third shell, n equals 3, L can be 0, can be 1, can be 2. So you have 3 subshells. All right. So you can see the number of subshell equal to the principal quantum number n. And the orbital here, 1, 3, 5, add together is 9, which is 3 to the second power. Okay, so the number of orbital is n squared. Okay, so in general, for a given principal quantum number n, there are n subshells and the total of n squared number of orbitals. They are all degenerate because all these orbitals, the quantum number n is 3, even though they have different L, different M, they correspond to the same n. And from last slide, we showed energy is negative 13.6 eV divided by n squared. So the energy is only depends on the quantum number n. And therefore, for hydrogen atom, 3s orbital, 3p orbital, 3d orbital, they all have the same energy. Put 3 here. Okay, same energy. So they are all degenerate. Now you may learn in Gen Chem that these 3p, 3d may have different energies. That's for multi-electron system. But for hydrogen atom, as we solve the Schrödinger equation, the allowed energy only depends on principal quantum number n. Therefore, these are all degenerate orbitals. Again, let's talk about the degeneracy. For hydrogen atom, the principal quantum number n can be 1, 2, 3, 4, 5. The allowed orbital angular momentum quantum number L can be 0, 1, 2 until n minus 1. Now for a particular L, M can be 0, positive, negative 1, positive, negative 2, positive, negative L. The maximum M is L. Now from last slide, we know under certain n, there are different L, different M, so you have different subshell. You have each subshell may have different orbitals. The total orbital number is n squared. And because they all correspond to the same quantum number n, so they have the same energy, they are degenerate. So the degeneracy is n squared for a particular n. So let's look at the example. When n equals 3, okay, what's the possible L? L can be 0, 1, 2. That's the 3s orbital, 3p orbital, 3d orbitals. So this is a shell, and this is a subshell. So 3 subshells. Okay, each subshell may have different orbitals. When L equals 0, there's only one M. Okay, M can be 0. So that's a 3s orbital. When L equals 1, then M can be 0, positive, or negative 1. So you have 3 orbitals. That's 3px, 3py, 3pz. Right? Now when L equals 2, then you have 0, positive, negative 1, positive, negative 2. That's 5d orbitals. So you have how many total orbitals? You have 1, which is s orbital, 3 for p orbital, 5 for d orbital, altogether 9. All these orbitals correspond to the same n, and therefore they are degenerate, okay, which is 9 degenerate orbitals. In summary, the wave function of hydrogen atom is a product of a radial function and an angular wave function, which is also called spherical harmonics. Each wave function is determined by 3 quantum numbers, n, l, m. N is called the principal quantum number, which can be 1, 2, 3, any integer. And it determines the energy of hydrogen, which is calculated by negative 13.6 eV divided by n squared. The angular momentum, orbital angular momentum quantum number L, specifies the magnitude of angular momentum and also gives the shape of angular momentum, or angular part of the wave function. L can be 0, 1, 2, until n minus 1. So the magnitude of angular momentum is calculated by h bar times square root L plus 1. The magnetic quantum number m defines the z component of angular momentum. M can be 0, positive, negative 1 until positive, negative L. And the z component of angular momentum is m times h bar. Now, there's a fourth quantum number that we haven't introduced yet, and that's called the spin quantum number. Spin quantum number can only have 2 values, positive, negative, half. And this is actually the quantum number specifies the magnitude of the z component of the spin quantum angular momentum. We have looked at the sum of the radial wave functions. For example, the 1s orbital, the wave function, radial wave function decreases exponentially when increasing distance. Does this mean the probability to find the electron is the highest at the center of the nucleus? And the answer is no, because the probability is not only depends on the wave function squared, but also depends on the size. Even though the probability density is the highest here, close to the origin, the size, the volume at the center is the smallest. So now let's define a related concept called radial probability distribution. Okay, this is defined as finding electron anywhere between 2 walls of a spherical shell of thickness dr at a distance r. So let's say this is nucleus, and at a certain distance r, there's a shell with thickness dr. Okay, the probability to find electron in this shell is calculated by the wave function squared times the volume of this shell. And in calculus, the volume of this shell is calculated by r squared dr sine theta d theta d phi. Now the wave function can be separated into the radial wave function and the sphere harmonics. Because radial wave function has no angle in it, so when we integrate along these angles, you can move out of the wave function, the integration. So the radial wave function squared, r squared times dr times all this integration along the angle d theta, sine theta, d theta, d phi. And sphere harmonic squared along all angle give you 1. And therefore you have the radial wave function squared, r squared dr. That's the probability to find the electron in this shell. Okay, the radial probability distribution is defined as this r squared, r squared. So you see the probability distribution is not only just the radial wave function squared, but you need to times the distance squared, and that gives you the probability distribution function. For example, for one s orbital, okay, here is the wave function. The radial probability distribution is the square of this times r squared. Okay, so how does this wave function look like? We'll see in the next slide. Again, this shows the 1s orbital wave function decrease exponentially when increasing the distance. And this is the equation to calculate the radial distribution probability distribution function for 1s orbital. Now, how does this distribution function look like? Before we plot it, we can calculate the maximum or minimum value of this probability. In calculus, the maximum or minimum can be calculated by the derivative of this function. And the derivative of this function, in this function, these are all constant. 4 and 1 over a naught cube are constant, so they can move out of the derivative. And so you have r squared times exponential negative 2r over a naught. So you can think about this as a composite function, u times v derivative equals u derivative times v plus u times v derivative. So we first derivative of r squared, that give you 2r times the e to the negative 2r over a naught, and then you times r squared and the derivative of the e to the negative 2r a naught, which is here, but then your derivative of the power give you negative 2r over a naught. Now you factor r times e to the negative 2r a naught, r, so r times this, and what you have is this function. So you have a bracket 1 minus r over a naught. So to calculate the maximum minimum, the derivative to be 0. So for this function to be 0, the only possible way is this bracket to be 0. All right, so 1 minus r over a naught to be 0. So 1 equals r over a naught, and therefore a naught must be r. So the distance r, okay, r is a naught, which is a constant 52.9 pm. So what is a naught? If you remember, in the introduction part, we mentioned that Niels Bohr proposed a model for the atoms, and that is the electrons has stationary orbitals. So you have different orbitals that have different fixed radius, and he calculated the first radius, and which is 52.9 for hydrogen, which nowadays we call a naught. So that's proposed by Niels Bohr. Okay, so interesting to see. Okay, if you plot the distribution of this one, the maximum probability is at distance a naught. So you can compare for all the quantum mechanics. The Niels Bohr proposed the fixed radius, and the first orbital is a naught. But here, for quantum mechanics based on Schrödinger equation, the electron can be anywhere, but the most probable place is just at the a naught that proposed by Niels Bohr. Here is a table shows the most probable radii for hydrogenic atoms or ions. For hydrogen, it's at the 52.9 pm. For helium ion, it reduced to 17.6. Lithium 2+ is similar, but beryllium 3+ becomes 13.2. Boron 4+ becomes 10. So the 1s orbital is drawn towards the nucleus, becomes smaller as the nuclear charge increases. Let's compare again the Bohr's model with the quantum mechanical calculation. In order to explain the atomic spectra, Niels Bohr proposed that electrons outside the nucleus has angular momentum and energy quantized, and the orbitals have defined radii. The first orbital has radius which is 5.29 times 10 to the negative 11 meter, which is called Bohr's radius. The quantum mechanics based on Schrödinger equation says that the electron can be anywhere. It does not have a fixed radius. The most probable distance, however, depicted by the dark color, is the same distance that an electron of Bohr's theory would have in its first orbital. This shows more radial probability distributions. For 1s orbital, we already see it has a maximum at A0. For 2s orbital, we see two maximums. A smaller one we call subsidiary maximum, a major one we call principal maximum. We also see a radial node right here, which we can visualize in this diagram, where the dark place is the maximum. In between, we see a radial node, the radial plane. Now in 3s orbital, this one, we see three maximums, a smallest one, a medium one, and the larger principal maximum. We have two nodes. One is here, one is here, and in this diagram, you have a radial node and the second radial node. And so, in general, for a wave function principal quantum number n, there are n minus L minus 1 radial nodes, as we already mentioned before. When you increase the quantum number n, for example, from 1s to 2s to 3s, the principal maximum are further away from nucleus. For 1s orbital, the maximum probability is at A0. For 2s orbital is right here, it's about 6 A0. For 3s is about 13 or 14 A0. So increase the distance of the maximum probability location. And for the same n, for example, n equals 3, the subsidiary maximum is closer to the nucleus with smaller L. In this case, n equals 3, 3s orbital, the subsidiary maximum is closest to the nucleus, and then the 3p orbital, and then the 3d orbital. So for 3s orbital, L equals 0, 3p, L equals 1, 3d, L equals 2. Okay, this has an important consequence for the energy of these orbitals. For hydrogen atom, these orbitals are all the same energy because they have same quantum number n. For multi-electron system, then these orbitals separate, becomes different energies. We'll see in the next section.